This is going to be a short but very important lesson. We're going to talk about L'Hopital's rule, and this is very useful tool to calculate the limit of transcendental functions. It goes like this. It works only for fraction and works with 0 over 0 type or infinity over infinity type limits. And it works like this. Limit of a fraction is the same as limit of the fraction given by the derivatives. Let's go with some examples. And here's an example. Let's go with this one. Limit as x is approaching to 0, secant of x minus 1 over x. If you plug in x equal to 0, the numerator is 1 minus 1, denominator is 0, so we have 0 over 0 type limit, but we cannot do any kind of factorization because this is not rational function. How can we handle that? Just take the derivative of numerator and take the derivative of denominator, and denominator will become really simple. Derivative of x is just 1. After taking the derivatives, just plug in and then we have an answer. So we end up with a trivial limit from that point on. Let's go with another example. This one, again 0 over 0 type limit. Oh, excuse me, this is infinity over infinity type limit. Plug in infinity, you have infinity square in numerator, denominator e to the infinity. So how do we work out? Take the derivative, and we have 2x plus 1 over e to the x. Still infinity over infinity. So take the derivative again. We have 2 over infinity, kind of like this. And now we have 2 over infinity, so the answer is going to be 0. So we can apply L'Hopital's rule twice. That's okay, because in this statement, the limit of fraction becomes limit of another fraction given by the derivatives. So if this one is unclear, you can apply it again for the second derivatives. Let's do this one more time. Let's plug in x equal to pi over 3. In that case, what do you have? Cosine of pi over 3 is 1/2, so we have 1 minus 1 in numerator. Denominator, sine of pi over 3 is square root of 3 over 2, so you're going to get, yes, 0 over 0 type limit. So how do we calculate this limit? L'Hopital's rule tells us to use derivatives. So let's take the derivative of numerator and then the derivative of denominator. Please note that we have to use a chain rule here. And then, do you see a cancellation? Yeah, the sine of x cancel out, and we ended up with a trivial limit. Plug in, and we have an answer. So, when you have transcendental functions, L'Hopital's rules are very useful. And it works only for fractions, 0 over 0 type, or infinity over infinity type. So, if you have product form, like 0 times infinity type limit, then you'll have to make it into a fraction to work out. The first example is relatively simple because e to the negative x power is actually the same as 1 over e to the x power, so you can readily make it into fraction form. Now it's fraction, and then take the derivative, and then we have an answer. Now this kind of problem is a little bit more challenging because it is unclear, because you see the previous problem e to the x, e to the negative x, that was clear. This time it's a little bit unclear. So how do you change this product into a fraction? Well, there are two ways. You can change that into log of x squared over 1 over x versus x over log of 1 over log of x squared. There are two ways to handle that, and it'll turn out that this one is okay and that one will be too difficult. You can change product into fraction by taking one of the factor forcefully into denominator by taking this reciprocal. But the problem is, if you take the derivative of this denominator, 1 over log of x squared, you'll see this is too complicated. And the purpose of this L'Hopital's rule is, after all, to make the limit simpler. If you made it worse than before, that's not the right way. So here we go. change it into log of x squared over 1 of x form, and then that one, as a matter of fact, is x to the negative first power, so the derivative for denominator is not too difficult at all. Derivative for numerator, of course, is coming from the logarithmic function and chain rule. 1 over the inside, and then the derivative of the inside is actually 2x. I missed the factor of 2. Okay, alright. And then after simplification, I get limit of negative 2x, but x is going to 0, so the answer is 0. So if you have 0 times infinity type limit, you can force it into fraction form, but often one way is right and the other way is wrong. If you got the wrong choice, do not just give it up. The other one must be correct. How about this one? Tangent of x times log of x. Well, tangent of x easily can be changed into denominator by putting into if I put tangent into denominator, it will become cotangent, so it falls into L'Hopital's rule category again. Derivative of log function is 1 over x. Denominator is going to be derivative of cotangent function. After that, we have a little bit of simplification, and then we can take the L'Hopital's rule again, and then we end up with 0. As a matter of fact, if students see this derivative of sine of x is limit of sine of x over x is 1, then this is going to be 1 times sine of x, that's going to go to 0. But that's okay, we can use L'Hopital's rule again to figure it out. So once you change it into fraction, then you can use L'Hopital's rule. What if you have even more calculated derivatives? Well, these are really advanced, but we have a little bit of time left, so let's talk about these. If we have some powers, you can use either change of base formula, or by taking log, you can change this into fraction. Here's one way. We just take the logarithm of this one. And then what do we have? By log rule, this x squared comes out, and we have x squared times log of x. But then again, you can change this 0 times infinity type limit into infinity over infinity type limit by log of x over 1 of x squared, and applying the L'Hopital's rule. So we got 0, but that's not the answer. The log of this thing was 0, so the real limit we are looking for is e to the exponential of that, so it'll be 1. Personally, I do not like this method very much because a bit too complicated, and then at the last moment something else to consider. So I like this one a little bit better. Use change of base formula, start from here, and then change base into exponential by changing by this rule actually. A to the b power is exponential b log of a. Change it over there, and then pass the limit to this power, and then we have the same thing again. Limit of x squared times log of x, so this is 0 times infinity type limit again. Use the same technique and you're gonna get e to the 0 power, and that's gonna be 1. Tougher integrals, but here they are, and some of these are equally as tough, some of them are a little bit easier, but all these are advanced problems, so I'll just leave them to interested students only. As for fraction type or 0 times infinity type limits, everybody should be able to do. These are, well, the minimal level problem, C level, and these are B level maybe. No, these are all standard problems. 0 over 0 type, infinity over infinity type, 0 times infinity type limit, all those are standard level problems. And then these kind of problems are a little bit more advanced, maybe A level, so I just de-emphasize in gray. Now we have still quite a bit of time, so let's talk about some L'Hopital's rule mistakes. Come on. Okay, failing to apply it properly. This is 0 times infinity type limits, so you have to change it to fraction, but I've seen some students just taking derivative times derivative. It doesn't work like that. You have to change it to fraction and then apply the L'Hopital's rule. Another common mistake, using quotient rule. Okay, I admit it, this is not really common. After L'Hopital's rule, students make mistake in quotient rule, take f prime over g prime. That's more common. But using quotient rule to L'Hopital's rule, well, that's theoretical, but I haven't really seen this kind of mistake while grading. But the other mistakes I've seen a lot. After L'Hopital's rule, people make mistakes in quotient rule. This kind of mistakes are a little bit more common, skipping the plug-in step. This one actually will turn out to be a trivial limit if I remember correctly, is it? Yes, just plug it in and then you have an answer. Yeah, okay, just plug it in. It's not trivial limit, it's undefined limit. But if you blindly use L'Hopital's rule, looks like you're gonna get something, but it is not. This is not 0 over 0 or infinity over infinity type limits. So if you do not plug in, then you may end up making this kind of mistake. I think the next one is gonna be no, this one is infinity over infinity type limits, but L'Hopital's rule is kind of inefficient in this case. So it works. Take the derivative twice and then you have an answer, although this is not really efficient way. But what if we have really higher order, 20th order for example? Take the derivative and we have 19th order, 19 more L'Hopital's rule to do. Not a good idea to do. Practical solution is to count all those growth order, 20th power, and then ignore the rest, and then you have the answer rather quickly. So this is something we did a long time ago, and then that's gonna be useful for L'Hopital's rule. Limit with radicals, those are the really important cases that L'Hopital's rule flat out fails. Do not try to think about L'Hopital's rule if you see a radical. They do not mix. If you try L'Hopital's rule to the derivative of numerator and denominator, you'll immediately see you made this limit worse than before. The basic idea behind L'Hopital's rule is to make the problem simpler than before. You made it worse. So what do? Just use your trick. Just take the highest order terms and then ignore the rest, and then just follow through and you're gonna get the answer. We have done this before and I hope everybody remembers. Infinity minus infinity type limit, again an example the L'Hopital's rule flat out fails. Looks like I do not have enough time to do any of the proof of the L'Hopital's rule, so let me explain it a little bit in simple terms, kind of like that, in naive terms. So L'Hopital's rule can be kind of manipulated like this. Insert minus 0 because f of a and g of a is 0, and divide by b minus a, and they look like the derivative. There's a bit of a problem. This quantity, if I take x to a, then it's not limit of f prime of x, it is f prime of a and g prime of a. So if you replace this one and that one by f prime of a, g prime of a directly, to a certain degree it works, but with this limit it does not. Of course there's alternative problem. What if those derivatives do not exist or denominator becomes 0? There are all kind of problems. So in order to prove it precisely, we need Cauchy's theorem, and that's gonna be rather too advanced, so I'll just leave it at that.